here is a proof of the Stolz theorem. So let's say if we have two sequences an and bn, if we want to work out the limit of an over bn, sometimes it can be an undetermined form. Could be positive infinity over positive infinity, or negative infinity over negative infinity. So as long as bn as a sequence is tending towards positive infinity and is monotonically strictly increasing. I've used the Stolz theorem in previous videos, but I forgot to mention that this is a condition must be met. Right? We require bn to be strictly monotonically increasing, otherwise it may not be true. Because first of all, I'll show why we need this condition. And as long as we can work out the limit of the an minus 1 over bn minus 1, if the limit of this exists, if this condition is met, then we can easily work out this limit is the same limit as this limit. So this is like a discrete version of the L'Hopital's rule, where we differentiate the numerator and the denominator, but instead, if it's sequence, we just work out their difference. And a could be positive infinity or negative infinity, or a finite number. And first of all, we need this lemma to help us to prove. So first of all, we're given a bunch of fractions, x1 over y1, x2 over y2, and xn over yn. And if we add up the sum, if we take the sum of all the numerators and divide it by the sum of all the denominators, and that number must be restricted in between the maximum, the biggest one out of all fractions, and the minimum fraction. And given that all the denominators are positive. And the reason why this is true is because, first of all, let me just denote the minimum of xk over yk, k from 1 to n, as c little m, and the maximum of xk over yk, k from 1 to n, as c capital M. And now let's look at the top, x1 plus all the way up to xn, right? So first of all, x1 plus xn can be written as, remember let's just denote xk over yk as ck. So in other words, xk can be written as yk times ck. So in other words, x1 is y1 c1 plus y2 c2 plus all the way up to yn cn. And if we just replace every c with the c capital M, right, the biggest one, right, then that is definitely less than or equal to y1 times c capital M times y2 c capital M all the way up to yn c capital M, and that is equal to c capital M times y1 plus y2 all the way up to yn. And if we divide everything by y1 plus all the way up to yn, we should have, because we remain the direction, because y1 plus is always positive, right? So in other words, we should have x1 plus all the way up to xn divided by y1 plus all the way up to yn is less than or equal to this also divided by the same thing, right? Divided by the same thing, then y1 plus all the way up to yn is cancelled out. And straight up we have just cm, right? that is the maximum out of all the fractions. And we're done with the right-hand side. For the same reason, the left-hand side can be easily done, right? Following the same logic. I'm not going to go through that. And then we can just work out our main theorem. If we want to work out this limit, then let's see if this limit exists, right? So, given that Bn is strictly monotonically increasing, right? If this limit is a finite number, then what will happen? So what's going to happen is that for any epsilon, right? For any epsilon, there is a capital N. Maybe n naught, right? Fixed n naught. As long as little n is bigger than n naught, then we have the following inequality: the absolute value of an minus 1 over bn minus bn minus 1 minus a, right, is smaller than epsilon. In other words, we just get rid of the absolute value and plus a on both sides. We should have an minus 1 over bn minus bn minus 1 is smaller than a plus epsilon and bigger than a minus epsilon. Right. For every n that's larger than this fixed n naught. Now, I'm going to fix capital N, which is larger than n naught. Then following the same inequality, I should have a series of inequalities, like a minus epsilon is less than just a capital N minus a capital N minus 1 over b capital N minus b capital N minus 1 less than a plus epsilon. And likewise, a capital N plus 1 minus a capital N over b capital N plus 1 minus b capital N is less than a plus epsilon, larger than a minus epsilon, so on and so forth. And an minus 1. A little n is fixed, large enough fixed. Bn minus 1 less than a plus epsilon, larger than a minus epsilon, where little n is also fixed but large enough. So like I said, we require Bn to be strictly monotonically increasing, because in that way we can make sure that first of all, every denominator is non-zero, right? Because if they were not strictly monotonically increasing, maybe two consecutive terms could be equal to each other. In that case, we could have 0 on the bottom. But since it's strictly monotonically increasing, then we don't have such problem, right? And also because it's strictly monotonically increasing, therefore every denominator is strictly positive, right? So we can just apply this lemma, right? Every yn is positive. In other words, I can treat every denominator as yn, right? y1, y2, right? yn. I can apply this lemma. So what's the sum of the numerators, right? Right, this is my x1 and this is my x2, right? Add them up. So first of all, it's easily a telescoping series, right? So first of all, an and minus an cancel out, right? And minus an minus 1, we keep it, right? This one stays, and this one, an plus 1 will be cancelled out with another minus an plus 1, in next pair. So in other words, after we cancel out the majority of the terms, in the end we're left with an, right, because an minus 1 will be cancelled out with the previous pair. So this one stays, and this guy stays as well. So according to this lemma, the sum of the numerators will become just an minus a capital N minus 1, and bn, for the same reason, bn minus b capital N minus 1 should still be less than the maximum of the fractions, right? Since, like I said, we fix capital N and fix little n, so we have finitely many terms here, so there has to be a maximum fraction, right? And since every fraction is in between this and that, so the maximum has to be in between this and that as well, and the minimum has to be in between this and that as well. So has to be still less than or equal to a plus epsilon, and still be larger than or equal to a minus epsilon. Right? Now, since that's true, I can just divide, because how can we translate this limit into this limit? Right? We want to work out this limit. All we have to work out is, so in other words, all I have to do is to divide everything by bn on here, right? So I have an over bn minus a capital N minus 1 over bn over bn is just 1. 1 minus divided by bn and b capital N minus 1, still less than or equal to a plus epsilon and larger than or equal to a minus epsilon. And in that case, we just multiply both sides by the bottom and plus the an minus 1 over bn, just cancel out this term. We can isolate an over bn. So like I said, we isolate an over bn. We have just an over bn is less than or equal to a plus epsilon times 1 minus bn minus 1 over bn plus a n minus 1 over bn, and larger than or equal to a minus epsilon times 1 minus bn minus 1 over bn plus an minus 1 over bn. Same thing. Then we can just simply take the limit infiniment on the left-hand side, right? Because remember, a and epsilon are fixed, right? And the limit infiniment of this term is just limit of this, because this limit exists. B capital N minus 1 is a fixed number, and Bn approaches infinity. Right? So this term approaches 0, and this term approaches 1. So approach a minus epsilon. And plus this term also approach 0. Right? So in other words, we easily have a minus epsilon is less than or equal to the limit infiniment n approaches the infinity of an over bn. First, I don't know if the limit exists, but limit infiniment always exists. Right? And we also know that limit infiniment is no larger than the limit supremum. Right? Limit supremum. Right, because what's the definition of limit supremum? Limit supremum is the supremum of the set of all the limit points, right? And limit infiniment is the infiniment of the set of all the limit points, right? Limit supremum an over bn. And we also take the limit supremum on the right-hand side. Right? So inequality remains less than or equal to, for the same reason, right? Limiting supremum is just limit, because the limit easily exists on the right-hand side. Right? A plus epsilon. Right, that's why here we take advantage of Bn approaching positive infinity, right, given condition. And now we see that inequality is always true for any given epsilon, right? And the limit confinement is now a fixed number, right? So a fixed number is always greater than or equal to a minus any epsilon. So since it's true for any epsilon, then we let epsilon approach 0, right? We let epsilon approach 0, still remain true, right? We let epsilon approach 0, still remain true, right? So in that case, limit environment is larger than or equal to a, and no less than limit supremum. Limit supremum is no larger than a. So therefore, limit environment is squeezed in between the same a. So limit environment has to equal to a, and so is limit supremum. So limit environment equal to limit supremum. So therefore, limit exists. So limit really exists, equal to a. Finite number in this case, like I said, could be also works for positive infinity or negative infinity. So like I said, a could be a finite number, but also true if a is positive infinity or negative infinity. Here's why. So since in this case, if limit an minus 1 over bn minus bn minus 1, this time if it's positive infinity, what will happen? Right. Since it's positive infinity, it means if n is large enough, then this fraction sequence can be large enough. Can it be larger than 1? Of course. Larger than any number, of course, can be larger than 1. So there exists a capital N. As long as little n is larger than capital N, then an minus 1 over bn minus bn minus 1 has to be bigger than 1. In other words, an minus an minus 1 could be bigger than bn minus 1. Right? For such little n that's bigger than capital N. So in other words, I have the following. A capital N plus 1 minus A capital N is bigger than B capital N plus 1 minus B capital N. And A capital N plus 2 minus A capital N plus 1 bigger than B capital N plus 2 minus B capital N plus 1. So on and so forth, until we reach some fixed little n where an minus 1 is bigger than bn minus 1, right? Again, we just add up all the left-hand side, right? Left-hand side, easily a telescoping series, right? Where a capital M plus 1 and the minus a capital M minus plus 1 cancel out. And a capital M plus 2 will cancel out with the next negative a capital M plus 2, the next pair. So in the end, we're only left with minus a capital N and a little n, right? That's what we're left with. So a little n minus a capital N is still bigger than or equal to b little n minus b capital N, for the same reason. So in other words, we have an is bigger than bn plus a capital N minus b capital N. And fixed, capital N is fixed, so is little n. Now in that case, since bn is already approaching positive infinity, and a capital N and b capital N is already a fixed number, right? So how about their sum? Of course, approaches positive infinity. And since this is already positive infinity, how about an? Right? An is bigger than positive infinity when little n is large enough. So in other words, an is really positive infinity as n approaches infinity. Right? So next question, is an monotonically strictly increasing? The answer is yes, because bn is given to be monotonically strictly increasing. Therefore, bn minus bn minus 1 is, of course, positive, and so is an minus 1. Therefore, an is, for any n, right, next term is always bigger than the previous term. Of course, an is also strictly monotonically increasing, right? Strictly monotonically increasing as well. So in this case, an actually satisfies this condition, right? So we can treat an as bn, right? So since we can treat an as bn, in other words, if the reciprocal, in other words, to work out if we want to work out this time the limit of reciprocal bn over an, right? Like I said, condition is that the denominator approaches positive infinity, right? Denominator. Now, we have the denominator approaches positive infinity, monotonically strictly increasing. Therefore, if we want to work out this limit, all we have to work out is just need to work out the limit of the difference between each consecutive terms, right? Just need to work out this limit. Then we can work out this limit. Do we know this limit? Like I said, we assume that this limit is positive infinity. Therefore, the reciprocal is approaching 0. Right? We know that this limit is 0. Therefore, we easily work out this limit is 0. In other words, the limit of reciprocal this time an over bn is, since this is approaching 0, and not necessarily every an or bn is positive, but as long as n gets large enough, every an and bn are positive because they both approach positive infinity. So this is approaching 0 from the right-hand side, right? So the reciprocal approaches positive infinity. We can definitively state that. And like I said, even if a is positive infinity, we can still state that as long as this limit exists, positive infinity, then the original limit an over bn is still the same limit, right? Still positive infinity. So even if a is positive, still true. So like I stated, like I've shown that even if this limit is positive infinity and still under the same condition, we can easily show that this limit is also positive infinity. Now, what if a is negative infinity? Right? If limit an minus 1, bn minus 1 is negative infinity this time, what will happen? Now, in this case, if we just multiply by negative sign on both sides, then meaning the negative of this is approaching positive infinity. Therefore, all we have to do is we let Cn equal to minus an, right? Cn equal to minus an. So in that case, the limit of Cn minus 1 over Bn minus 1 is in fact just negative of An minus An, quantity An minus 1, right? Obviously approaches positive infinity, right? Under this condition. Then, using our previous demonstrated fact that it's true for positive infinity, therefore we easily state that the limit of Cn over Bn is also the same limit. Same limit. Therefore, the limit of, because Cn is negative An, right? Negative An. If we just multiply by negative sign on both sides, then we just say easily An over Bn is easily approaching negative infinity. Now this time using our Stolz theorem, we can easily work out the previous Cauchy proposition, which I've proved in a previous video using a different method, epsilon capital N. This time we can use Stolz theorem and easily, quickly prove it, that if the limit of An is equal to A, then we can easily show that the limit of the arithmetic average of the sequence also approach same limit. Why? Because in order to work out this limit, all we have to show is that, first of all, n is my Bn, right? Bn, is it strictly monotonically increasing to positive infinity? Yes, obviously. And there's no restriction to the numerator, right? It could be a finite number, could have a limit, could approach to positive infinity, could be jumping in between 2 points, whatever. So all we have to show is that this limit exists, right? Does this limit exist? So what's Bn minus 1? Bn is n, Bn minus 1 is n minus 1, right? Their difference is just 1. Right, what's An minus 1, right? In fact, in this case, An just means A1 plus all the way up to An, right? An minus 1 just means An plus all the way up to An minus 1. Their difference is just the last term of this sum, right? It's just An. Does this limit exist? Yes. Right, we're given that this limit exists. Therefore this limit also exists. Same limit. Right. And so previously using epsilon language, we require A to be a finite number, but using Stolz theorem, we don't even require A to be a finite number, right? Even if A is positive infinity, this is still true, right? Using Stolz theorem. And notice that the inverse statement may not be true. In other words, if this limit exists, it doesn't necessarily mean that this limit exists. Right? The reason is because if I say an is, let's just say this sequence looks like this: 0, 1, 0, 1, all the way up to infinity. And let's say Bn is equal to n. Right? Now, even if this limit exists, right? So does an over bn? What's the limit over an over bn? First of all, bn approaches infinity, and an is a bounded sequence, right? Bounded sequence over positive infinity, of course, approach 0. Now, even if this limit exists, like I said, it doesn't necessarily mean that this limit exists. The reason is because what's an minus 1? Right? It's either going to be 1 minus 0, that is 1, or 0 minus 1, that's negative 1, right? So it's, right? There's no definitive number. It's only positive or minus negative 1. But what's bn minus 1? That is just 1, right? Because it's n minus 1, that's 1. And so does this limit exist? No. It turns out to be jumping in between positive 1 and negative 1, so there's no limit for. So the inverse statement may not be true. But if we add some additional condition, it may be true, which I will probably demonstrate in a future video.